Welcome. This is a test review for Chapter 3. I'm only doing this pre-recorded because I feel like a lot of you do need some extra practice with some of these problems. So I'm just going to go straight through and work them, but I would suggest that you pause them and then watch my work. Like pause them, try them yourself, and then watch my work. Okay, this would be synthetic division. So I'm going to take the divisor, set that equal to 0, and I'm going to get 2. And so that's what's going to go in here. So I'll bring the 2 down, I'll multiply, add, multiply, add. And so when I do that, I'm going to get, when I write this out, I'm going to decrease my power by 1. So I'm going to have 2x plus 1. And then my remainder is going to be 6. So I'm going to write 6 over x minus 2. Okay, on this one you can use either synthetic or long division, and synthetic would be easier because there's no squared term here. So I'm going to do a -3, so set that equal to 0 and get the -3. Always remember if you're missing any terms to put zeros as placeholders. So I'll bring the 2 down, multiply, add, multiply, add, multiply, add. Okay, so I started with a cubic equation. So when I write this, I'm going to drop down to a second degree polynomial. So 2x squared minus 2x plus 4. And then the remainder is going to be -13 divided by x plus 3. Okay, on this one, you are given a polynomial and you're told to write the polynomial of the third degree. So when I look at this, I can see that it does have an odd degree polynomial with a positive leading coefficient. It has zeros at -1 and 2. So I'm going to have p of x equals x plus 1 and x minus 2 because I need to take each of these zeros, which is -1 and 2, and I'll do x minus the 0 to convert it to a factor, and then I get these factors. So if I multiply this out, this would be a second degree polynomial. So when I look at this, I see that it crosses here, which tells me that's an odd multiplicity. Here it touches, so that tells me it's an even multiplicity. So because it's an even multiplicity, this is going to need to be to an even power. So this will be to the second power, and that way I have an x to the second and an x to the first, and if I multiply those two together, I get an x to the third, which is what I'm looking for. Okay, this one, you are given these zeros, you're asked to show this and then to find your other zeros. So I'm going to show this using synthetic division. So I'm going to do -1. I'll put my coefficients down. Okay, so I'll bring it down, I'll multiply, I'll add, I'll multiply, I'll add, then multiply, multiply, and I get 0. And 0 is what I would expect since this is a 0 of that polynomial. So I'm going to turn around and do the same thing again. So, but this time I'm going to do this with the 4. So I'll bring the 2 down, I'll multiply. So go through this synthetic division process. Again, I come out with a 0. So here I'm at a fourth degree polynomial. I'll reduce it down to a third degree. And then finally at this point I'm at a second degree. So this is going to be 2x squared minus 11x minus 6. And in order to find our other zeros, I need to either factor this if it factors or use the quadratic formula. So the quadratic formula is going to give me okay, and so that's going to simplify to be the square root of 169 over 4. So 11 plus or minus 13 over 4. 11 plus 13 is going to give me 24 over 4, which is 6. 11 minus 13 will be -2 over 4, which is -1/2. So the other zeros are 6 and negative 1/2. Okay, here's another one to do. If you go through, we'll do -3 first. Doesn't really matter which one you do first. Okay, so then we'll do the 4. Okay, so we've got a 4x squared minus a 7x minus 1 that we need to do the quadratic formula for. So we're going to have negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. So that's going to be 7 plus or minus the square root of 65 over 8. Okay, I'm using synthetic division and the remainder theorem to evaluate P of C. So we're just going to put this in our box here to evaluate this. Okay, so negative 10 would be the value of that. And that's going to be the same thing we would get if we plug negative 1 in to this. It's just the remainder theorem tells us that if we do synthetic division and divide negative 1 into it, that whatever we get here as our remainder is the same as evaluating the function at that point. Okay, here's one using synthetic or long division. It actually has to be long division because the square here. So we're going to have 2x squared plus 0x plus 1, and we're going to divide that into 10x to the fourth plus 4x to the third plus 7x squared plus 0x plus 0. So here I'm going to multiply 2x, or see what multiplies by 2x squared to give me 10x to the fourth. So that's going to be a 5x squared. I'm going to multiply that through. So 5x squared times 2x squared gives me 10x to the fourth plus 0x to the third plus 5x squared. Change the signs of everything. These will cancel, and I'll have 4x to the third plus 2x squared. Bring this down, so plus 0x. Now I need to see how many times 2x squared goes into 4x to the third. So that would be 2x times. Multiply that 2x times all of this, and I'll get 4x to the third plus 0x squared plus 2x. Change all the signs, and I've got 2x squared minus 2x and bring the 0 down. Okay, my degree here equals this degree, so I've got to go one more time. So I'm going to multiply it by 1 times 2x squared gives me 2x squared, which is what I want. So multiply that all the way through. Change your signs. Okay, so I'm going to have a remainder of negative 2x minus 1 over 2x squared plus 1. I know I can stop at this point because the degree of this expression is less than the degree of my divisor. Okay, here we're asked to find all the zeros of the polynomial, which would basically in some cases mean factoring, but this one is a 4-term polynomial and our only method of factoring is grouping, and if you try grouping, you're going to see that it doesn't work. So what you're going to need to do is actually put this in your calculator and find the real zeros first from that. So the sketch of the graph on that one actually looks something like this. And it's touching here at -1. We also know that because it touches that it has an even multiplicity. So it's not just negative 1 one time, it's negative 1 twice because of what we see here on the graph. So I'm going to do negative 1. Be sure that you put 0 in for the missing term here. And we'll go through and do our synthetic division. And we get 0, which is what we would expect. So we're going to do it another time because it had a multiplicity of 2. Again, we get 0, which is what we expect. So we started with the 4th degree, we reduced it once to a 3rd degree, and now we're at a 2nd degree here. So we've got x squared minus 2x plus 2. And if that factored, we need to factor it. I know from looking at this that it's not going to factor because the graph shows me all of its real zeros, and therefore there are no other real zeros. So that means the zeros that come from this are going to be complex. So I'm going to do negative b plus or minus the square root of b squared minus 4ac over 2a. So I've got 2 plus or minus the square root of negative 4 over 2. If you remember, the square root of negative 4 is 2i. And when we simplify that, it's going to be 1 plus or minus I. So one thing, if it says enter all answers, including repetitions, so I would need to list this one twice in order to have the answers that I need listed here for WebAssign. So just be really careful about that. Okay, here, if you're going to find a polynomial with integer coefficients that satisfies the given conditions, we need to take each of these zeros and turn them into factors. Okay, so we're just going to do x minus each one of these. When I'm going to need to multiply it out to integer coefficients, the easier thing to do is to multiply the two factors together that have the complex conjugates. So this is going to be x squared. The inner and the outer terms will cancel. So minus 4i squared. So this is going to be x squared. I squared is equal to negative 1. So it's going to be plus 4 when I simplify this. Okay, now I'm going to bring this down and multiply this out. Okay, and then that's going to be our polynomial. Okay, we could do the same thing here, except they only give us one of these, but you need to remember that they come in complex conjugate pairs. So even though they're saying I, we also have negative I because negative I is its conjugate. So I'm going to turn each of these into a factor. Okay, and then I'm going to multiply these that are the complex conjugates together. Bring this one down. This is just x. So I'm going to end up with x to the third plus x for my answer. Here you're asked to find all the zeros of this polynomial, so it's not going to factor. So I'm going to go straight to my graph. When I look at the graph for this one, the graph actually crosses at 3. So it's going to look something like this, not a straight line, but a curve. So 3 is the 0, so I'm going to put 3 in and reduce this down. I'll multiply and add and go through this division process. So I'm going to reduce it down to x squared minus 4x plus 5. I know it's not going to factor over the real numbers because there's no other real zeros that show up here. So I may as well go ahead and use the quadratic formula. So that's going to be negative b plus or minus square root of b squared minus 4a and c over 2a. So I've got 4 plus or minus the square root of negative 4 over 2. So 4 plus or minus 2i over 2. And if I simplify this, 4 over 2 is 2. 2i over 2 is just I. And so those are my answers. So if I'm listing all of my zeros, I'm going to go back to this real one that I found, and then I'm going to list these complex ones here as well. Okay, on this one, we're going to start with x to the 4th plus 9x squared. This one does factor, so I'm going to have x squared times x squared plus 9. I'm going to set each factor equal to 0. And I'm going to get 0 and plus or minus 3i. This 0 has a multiplicity of 2 because the x is squared. So I'm actually going to have 0, 0, 3i, and negative 3i as my zeros because it does want me to include repetitions. Whatever my degree is, I'm going to have that many zeros. Some of them may be repeats, but I'm still going to have that number of zeros. Okay, for factoring it, once you have the zeros, you want to take each one of these and turn it into a factor. So we'll have x minus 0, x minus 0, x minus 3i, and x plus 3i. This part here could just be reduced to x squared. And so this is going to be my polynomial factored here. Okay, quadratic functions, putting it in standard form, you do need to be able to show me the work for this. So we're going to have f of x equals 3x squared minus 18x. We always want to take the constant and push it over to the side. Then we want to take out our leading coefficient. Okay, for this one, I'm going to take my b, divide it by 2, and square it. And so that's going to give me 9, and that's what I'm going to add here. So I'm going to put a 9 in here. Because I just added a 9 that's multiplied by a 3, I just basically added a 27. So I'm going to offset that with a negative 27. This will always factor to be x minus something squared. So in this case, x minus 3 squared, and then minus 39. So this is going to be the standard form for this particular function here. The vertex is going to be 3, negative 39. Think of this as, going back to translations, this is a parent graph of x squared, vertically stretched, shifted right 3, and down 39. So if the standard parabola starts at 0, 0, and it's shifted right 3 and down 39, then its new vertex is going to be at 3, negative 39. For the x-intercepts, we are going to find an x-intercept, we always put 0 in the place of the y, which in this case is the f of x. So I'm going to have 0 equals 3x squared minus 18x minus 12. If that factors, that's great. This one I don't think does. So we'll have negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we're going to have on that, I think this is 468. Over 6. And really the only other thing we can do with that is to do, we can take a 2 out from underneath the radical. It's still pretty messy. Okay. So don't give it as a decimal unless WebAssign specifies the correct number of decimal places to round it to. Otherwise, just give it as the radical answer. Okay, for the y-intercept, we always let x equal 0 to find the y-intercept. So we're going to plug 0 in for x. We're going to get negative 12 for the y-intercept. For the domain, this is a quadratic, so we don't have radicals, we don't have denominators, so the domain is going to be all real numbers. And then for the range, we know what the vertex is. The vertex is 3, negative 39, and we know it has a positive leading coefficient, which means it's opening up. So the lowest value that it goes to is this negative 39. So my range is going to be from negative 39 to positive infinity. Okay, on one like this, where you ask to find the maximum or minimum value, you could do that by putting it in standard form. But if all it's asking for is the maximum or minimum, the easiest thing is going to be to find the x coordinate of your vertex by doing negative b over 2a. So that's going to be we're going to have a negative 6 over 2 times negative 3, which will give us 1. So our x coordinate of our vertex is 1. We'll plug that back in. And when we plug that back in, we're going to get 13. So this one, it is going to be a maximum because we know that we have a negative leading coefficient. That means that it's going to be opening down. And since we have it opening down, we have a maximum. And if it's asking for the maximum value, the value is going to be the y coordinate. So that's going to be 13. Okay, on one like this, again, this is one that you would not want to put in standard form. So we're just going to do the negative b over 2a. So I'm going to have negative 5 over 2 times negative 0.001. And that's going to give me 2500. I'm going to plug in 2500 into the equation. And I'm going to get 4,375. Okay, so we need to identify in terms of the x and the y, which in this case is the p of x, what they represent. So x is representing, and it tells us in the problem, x represents the number of cans, and p represents the, so x is representing the number of cans, and so p, the y is representing our profit. So our coordinates for our vertex is going to be 2500, 4375. So this is going to be our number of cans, and this is going to be our profit. Okay, so what's the maximum profit per day? That's going to be the 4375. And how many cans is going to be the 2500 cans. Okay, if a ball is thrown directly upward with a velocity of 24 feet per second, its height after t seconds is given by this. What is the maximum height attained by the ball? First thing I would do is put it in general form, where we have the t squared first. We want to find the maximum height. So we know that this is a parabola that's opening down, so we just need to find the vertex. So the vertex is going to be negative b over 2a. So negative 24 over 2 times negative 16 will be 0.75. So then we're going to plug in 0.75 to our equation. And we're going to get 6. So our coordinates of the vertex is going to be 0.75 and 6. If you read back up here, t is your independent variable, and it's measured in seconds. So this is going to be our time in seconds. And then this is going to be our height, and that's going to be measured in feet. So what is the maximum height? That's going to be this 6 feet is going to be the maximum height. Okay, for this particular function, find the zeros with their multiplicities, the y-intercepts, the end behavior, and choose the correct graph. So looking at this one, our zeros, we get 1 0 from this, so that 0 would be negative 1. This 0 is going to be positive 1, and this 0 is going to be 2. So the multiplicity for the negative 1 is 2 because that's its power. The next multiplicity is 3, and then this one has a multiplicity of 1. As far as the y-intercepts, what we're going to do to find the y-intercept is we just plug 0 into this equation. So we're going to have 0 plus 1 squared times 0 minus 1 cubed times 0 minus 2. So we're going to have negative 1 squared is 1, negative 1 cubed is negative 1, and then here we're going to have a -2. So we're going to have a -2 as our y-intercept. Okay, this one, looking at the end behaviors, our degree, if we look at these powers, we've got a 2, a 3, and a 1. So when we multiply our bases, we add our exponents. So we're having a degree of 6. So we have an even degree, and we have a negative leading coefficient. So if I have a negative leading coefficient and an even degree, then my graph is going to be opening down. So it's going to have to be either this graph or this graph. We can eliminate these because of it needing to open down. We need to check our zeros. So at -1, it has an even multiplicity, so it should be touching, which both of these are. At +1, it has an odd multiplicity, so it should be crossing. So that one is, and this one is. And then at 2, it should also have another 0. So this one does not. So we're going to eliminate this one. So this looks like it would be our answer. As x goes to infinity, y is going to be going to -infinity. Okay, so here we've got one, factor the polynomial and use the factored form to find the real zeros. This is one that we actually can factor. So I'm going to factor by grouping. Okay, so I'm going to have an x plus 5 and x squared minus 4. This can factor a little further. This would be x minus 2 and x plus 2 because we've got the difference of squares. And so from this factored form, I can find my zeros. The 0 here would be -5, 2, and -2. So if it factors and we're looking for real zeros, that's pretty easy to do. Okay, determine whether -2 is a factor. And so to determine if it's a factor, I'm going to set that equal to 0 and I'll get 2. I'm going to put that in here and then do synthetic division. I want to show that my remainder is 0 and then therefore it would be a factor. Okay, so I'm going to drop the 1 down. I'm going to multiply. Okay, and because that's a 0, then that shows that x minus 2 is a factor. Okay, find a polynomial of degree 5 that has these zeros, and I said you don't have to multiply it out. So we're going to have this polynomial. The first 0 is -5. So the factor that goes with -5 is x plus 5, and it has a multiplicity of 2. We have the factor 0 with a multiplicity of 2 also, and then we have the 0 of 4 with a multiplicity of 1. So I am going to kind of clean this up a little bit. I'll have x plus 5 squared. This would just be x squared and then x minus 4. Typically in x squared, we don't like it buried in the middle here. We're going to pull that out in front. And so this would be the polynomial to represent that. I'm not going to ask that you multiply something like that out, so that's fine to leave it in that form. Okay, find all the zeros of the polynomial. This is actually a repeat problem, so I'm not going to go back through that. You can watch the earlier one in this video. Here, find the x-intercept, y-intercept, vertical asymptotes, and so forth. This is a rational expression, so to find the x-intercepts, we're going to look at the numerator. So we're going to set that numerator equal to 0. And so our coordinates are going to be -4, 0. So what I'm going to do is I'm going to come over here and I'm going to start building my graph, and I'm going to put a x-intercept here at -4, 0. My y-intercept, I'm going to plug in 0 to the equation. So I'm going to have 4 over -5. So my y-intercept is going to be 0 and -4/5. Okay. All right, my vertical asymptotes, those come from the denominator. So I'm going to set my denominator equal to 0. Okay, so these are equations of lines, not points. So I'm going to come over here and I'm going to draw a vertical dotted line at -5, and I'm going to do the same thing here at 1. Okay, for my horizontal asymptotes, these are the 3 rules you need to look at for comparing the degrees. It's an easier way to look at this if we go ahead and multiply this out. So this is going to be x squared plus 4x minus 5 if it's multiplied out. So what we see is that the degree of the numerator is less than the degree of the denominator. And I'm not going to go back through those rules here. You can go back and look at the video on section 3.6, the first part, and it does have those rules listed for you. So if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is going to be at 0. So I'm going to go in and I'm going to put this horizontal asymptote, which is a dotted line, across here. Okay, from here, I'm just going to fill in the graph. So if I go and I look at my calculator, when you enter this in the calculator, make sure that you group this denominator together or it's not going to give you the right graph for this. But the graph looks something like this. It's going to stay pretty close to these asymptotes across here and the vertical asymptote as well. This one's going to stay close to the asymptote, come and pass through these points, and then get close to the asymptote again. And then this one's going to be up here like this, again, kind of hugging the asymptotes with that. So this is what my graph would look like. As far as the domain goes, the domain is going to be on this one. It's going to correspond with my vertical asymptote. So whatever my vertical asymptotes are, that's the values the domain cannot be. So we want to write that in interval notation. So it would be -infinity to -5. -5 to 1, and then 1 to infinity. The range on this, you just want to look at your graph, and since we have this middle part here, that's going to indicate my range is -infinity to +infinity. If I did not have this middle part and I only had this part and this part, then I would need to exclude here at the horizontal asymptote. Okay, find a polynomial with integer coefficients that satisfies the condition. You can practice this one. I've already gone through an example like that, so I'm not going to do another one here. Okay. This one, identify your horizontal asymptotes. If we look at this, we have degrees that equal each other. So in that case, we want to look at the ratio of the coefficients. Horizontal asymptote is always y equals, so y equals 3/2. Okay, this one is talking about vertical asymptotes and holes. So the first thing you want to do here is to actually factor this. So it's going to be x plus 3, x minus 1, and this is going to be x plus 3, x minus 2. So these are going to cancel, and we'll have x minus 1 over x minus 2. So what we see is that we get a cancellation here, and so this tells me that I'm going to get a hole at x equals -3. So I definitely have a hole at -3. And then looking at this, I want to look at the reduced one. Okay, so this is what we're going to call our reduced equation or a reduced function. Okay, so our reduced function is going to give us our vertical asymptote. So our vertical asymptote is going to be set the denominator equal to 0, and we're going to get 2. So we have a vertical asymptote at 2, and we have a hole at -3. So our answer on that one is going to be C. If you had to carry this a little bit further and like find the actual coordinates of the hole, what we would do is plug the -3 from the location of the hole. We're going to plug that into the reduced function. So we would have -3 minus 1 over -3 minus 2. So -4 over -5, which is 4/5. So the coordinates of the hole itself would be -3 and +4/5. Okay, so this one you're actually asked to find the hole for this one. So we'll again factor this. So this is going to be +3 and -2. This one's going to be +4 and -2. So we can see the x minus 2's will cancel, so our reduced function is going to be x plus 3 over x plus 4. our whole is going to be at, look at the canceled factor. So the whole is going to be at 2. So I'm going to plug 2 into this reduced function. And I'm going to get 5/6. So the whole is going to be at 2 and 5/6.